Now I'm going to tell you about a model for thermal energy, a microscopic model for thermal energy. Microscopically, you can see there's a bunch of atoms. This is a gas of 100 atoms running around in this box here. Simulation isn't started yet, so you can't tell that they are currently moving, but if you looked up here at kinetic energy, you would see it's positive, so something in there must be moving. In fact, they're all moving. Because this is a gas, the potential energy is negligible, so the only energy, the total energy, is equal to the kinetic energy. There's only kinetic energy here. So what I'm going to do is add energy to this gas in steps of 1 times 10 to the minus 21 joules. That's about twice as big as the kinetic energy is already, so this initial kinetic energy is very low. You can see that there's going to be 500 frames. I'm going to add 1 times 10 to the minus 21 joules of energy every 100 steps. So the first 100 are going to be with this energy. You'll be watching them move around. The second 100 is going to be with this energy plus 1 times 10 to the minus 21. Steps 200 to 300 will be with another 1 times 10 to the minus 21 joules of energy. Steps 300 to 400 will be with another 1 times 10 to the minus 21 joules of energy. So the energy is just going to keep going up. The temperature will keep going up because there are 3 independent kinetic energy modes for each atom. They live in a 3-dimensional box, so they live in a 3-dimensional world. So there are 3 modes per atom. There's 100 atoms, so there's 300 modes altogether in this box. And each of them, by the equipartition theorem, each of them gets an energy, Boltzmann's constant times the temperature divided by 2. If you take this temperature that's sitting here right now, that's 0.19, the initial temperature. If you take that temperature, multiply it by Boltzmann's constant, divide by 2, multiply by 3 for the number of modes per atom, and then multiply by 100 for the number of atoms. So you get the total number of modes is 300 times this number here. You will get the 4.08 times 10 to the minus 22 joules. So let's just watch this thing go through as I add in energy every 100 steps. So the first 100 steps, I have the initial energy. The second 100 steps, higher temperature, faster. The third 100 steps, higher temperature, moving faster. The fourth 100 steps, higher temperature still, moving faster still, and that'll be the end. So we move from 0.19 Kelvin up to, oops, I forgot the last one, up to 2.09 Kelvin. 2.09 Kelvin is the temperature we're at the end. I'm going to do the same thing with a solid. Same thing, 100 atoms. Each atom moves in a 3-dimensional world. So there's 3 kinetic energy modes per atom. So there's still 300 kinetic energy modes in the solid. You could say that those 300 kinetic energy modes are all vibrational modes. They are, because there's only vibrations. The atoms just vibrate back and forth. They have kinetic energy, but they're not flying freely. They're bound into the solid, so they're vibrating back and forth. Because these are vibrational modes, each of them comes complete with a potential energy mode, a spring-like mode. So there's a total of 600 modes per atom. I started this out at the same temperature, so the kinetic energy is going to be the same because there's still 300 kinetic energy modes. But there are 300 potential energy modes, so the total thermal energy is going to actually be twice this kinetic energy. The potential energy is the big negative number because of the bond energy. These things are bound together, so you can't read the thermal energy out of here, out of this potential energy very easily, because it includes bond energy. In any case, I'm going to do the same thing. I'm going to start this simulation, and every 100 steps I'm going to add 1 times 10 to the minus 21 joules. So let me start it up, and we'll see the temperature change every 100 steps. So it's at 0.19, coming up on 100 steps where I add the first. It changes to 0.43 about, and at 200 it is changed to 0.67. At 300 I add some more. You can see the whole thing going a lot faster. Temperature is about 0.9, and then at 400 it moves faster, and the temperature, well, it says 1.19. I was guessing on average it was about 1.15 Kelvin. So the gas went up to over 2 Kelvin. The solid only went up to 1.5 Kelvin, even though they started at the same place, and I added the same amount of energy. The reason is that the gas has fewer modes. So when you add energy, here's the graph. When you add energy, this is on the horizontal axis, when you add energy to the gas, the temperature goes up more than it does for the solid. And in fact, it goes up twice as much because they each have 100 atoms, and the solid has twice as many modes. Same number of kinetic energy modes, 300, but also has the 300 potential energy modes. So the solid's temperature doesn't change as much for the same delta E, and the heat capacity is delta E over delta T. The heat capacity for a solid, because delta T is smaller for the same delta E, the heat capacity for the solid will be larger. It's larger, in fact twice as large, because it has twice as many modes. The heat capacity is proportional to the number of modes, the number of places to put energy.